Okay, let's jump straight into our advanced concept one. And this is again, we're back at elastic strings and springs, or springs and elastics. And we're not going to go into the details. I'm going to assume you know Hooke's law, you know how to statically balance forces and things like that, and going straight into the part that matters here. And there's two pieces. One is what do elastic strings and springs do in dynamic environments, meaning objects moving, and the other is about energy. We'll start with the first one. Okay, I will go in here. Actually, let me illustrate this with here. Obviously, I have the string here. It's elastic. Um, First things first, if I had a little small object here, I stretched it, you studied the static forces that appear, but if the moment I let go, what happens? The chalk starts moving, and it is that which we want to study. So we're going to start off here, and I'll go with my string. Remember, the same applies to a spring as well, and I'm going to start here with what I call the natural length M, natural length L. The object is mass M. We know for every elastic string there is a modulus of elasticity lambda. Okay, and obviously you also have a relationship with tension, but let's now start with this. Acceleration due to gravity doesn't change, so we got that. We know that value. We know that. We know that, and there we go. So what's happening here is a natural force exists that's going to pull this. So as soon as I have M attached, what I will see is this is L, and because of M, there is an extension of X, right? So we have another variable there, and you know the math. If this was an equilibrium, tension force T, so maybe the way to write it, what we learned before is T tension is equal to lambda x by L, and that in this case is nothing but balanced out with mg. Now, let's say I apply a force, additional force here, and I'm going to call this force, just for the purposes of my talk here, this is going to be just force F, right? I'm just going to apply a force of F newtons, right? And I'm going to take this out. So think of it classically as a case where I am, obviously the chalk's there. This would be the case, and I'm applying this force here, right? And I will actually use another color just to show you that there is, so you're not confused. So I'm applying force F, right? Equilibrium of forces should tell you now that T is equal to lambda x by L, which is equal to that plus mg, right? If you don't know this, go back to core concepts and look at what equilibrium means. But that's the idea. So if I have an object M and I apply a force F, then that would be the equation for the same level of extension that you see. Now, the point is, what happens if I suddenly let go of F? F goes to zero instantaneously, right? What happens to the object M, right? At the very moment of release, this is what I want you to think of. So again, visualize it this way. Visualize it this way. At that moment when I let go, wow, it just shot up. Hopefully it didn't damage the lights upstairs, but up there. So at that very moment, what happened? There was an incredible amount of force that acted on the tiny chalk, shooting it up, right? Obviously, it was not attached to the string. If it was, then it would have some, it would be restricted and it wouldn't just fly away. But let's just look at what happened there. I'm only going to speak from the effect of forces, right? So we're back to that picture. Mass m, natural length L, an extension x, with a balance of force of T and mg and F, with F applied here. At that very instant when F disappears, I'm just going to take F. What's going to happen? T is still that much, but the force on one direction, which is only mg now. So the net of forces is really the net force that the object experiences is really, think about it, the same as F, but I could write it as the tension that it experienced minus mg. Work with me on this one. And if that was the tension, and at that very moment it was experiencing an acceleration that was basically T minus mg divided by its mass. With me so far? What happens to acceleration when applied to a body that was at rest? It begins to pick it up and take it up, so u, initial velocity here. So the moment F is gone, initial velocity here is u equal to 0. The object starts accelerating in this direction, right? Which means it gains velocity and it goes up to a point, and at that point it's gonna, there's, if you think about it, and let me state it this way. At that point, its velocity is going to go down, and then the object, of course, goes to free fall and comes down. Or if it's attached to the spring, it will again come back and forth. Now here, I just want you to work with this idea that I have this spring or this string, right? And let me just say it's attached here. There's my object first. There's my object going back up to a point where it stops. Now this, I will do it with a dotted line. So somewhere here, it's got a velocity v, and then it comes to a point where v is equal to 0. And it has traveled some length. Now this total length is L plus x. That hasn't changed, but this has traveled some length. We don't know how much. We don't know how far it has gone. And it has taken some time for it to happen, right? Some time has lapsed for this event to occur. If you now said that there was instantaneous acceleration, right? Because there was a single force acting this way. Work with me to say that as the string retracted, x became smaller. If x became smaller, I'm going to write this here, tension is always equal to x by L. X became smaller as L stays the same, tension kept reducing to a point where that tension equated mg, because mg doesn't change, the object always has the force of gravity that's pulling it down. Tension keeps reducing as x is lower, At a point, it becomes equal to mg, which then makes acceleration 0, which means velocity has kind of peaked. And if I was going to do this with the time here and velocity here, what I'd see is instantaneously there is acceleration. It drives the velocity up. It peaks it out at a point. Velocity is maximum at a particular point. So if you get a problem that says find out at what distance from here, or at what extension, what extended length does velocity become maximum, then that is that value of tension equal to mg. You'll get your x and you'll know that's where you need to be. I'm going to let you work on these problems. I'm giving you the context for it and helping support the idea here, right? But you can take this several steps forward. You can even then continue to work the math and say, okay, now what happens? Why does it become 0? Well, it becomes 0 because there's deceleration, because as tension goes down to 0, negative mg. Negative mg is what? Negative force, which means the direction of the acceleration is different. We remember from core concepts, early in core concepts and basic concepts, the negative direction means it's a deceleration to 0. If you remember your equation of s is equal to ut plus half at squared, you can work out if acceleration is negative, then as time progresses, you will keep reducing your distance. Basically, you're eating into velocity here, right? So you can work out these, you know these equations from before, but this is how you develop the math behind the motion of this object. What happens, likewise, there is deceleration to a particular point, after which, velocity begins to drop. So right at acceleration peaks, velocity drops as the object comes back to rest, right over here. And of course, after that, it's again just gravity acting to bring it down, because then the net effect of gravity becomes higher. You no longer have t minus function there. There is no t, and your motion gets reversed. You'll start experiencing increasing velocity, right? Hopefully that gives you a good picture. What I'd like you to do as an exercise is build some of these equations. Try and build a value of x. In this particular instance, a value of x for a given function t, if you know what f was. So try and express either t as a function of f, for example, whatever was the initial force. You can play with this a fair bit, but you get the idea. Try and estimate x when velocity becomes 0, and do it for different types of elastic strings. You can flip it around and make this as an extension of a spring or a compression of a spring. Or if you want to give yourself some more fun, you can just make this a string and a spring. Okay, and you can call that y and see what happens. If you have these two objects, right, and they're both connected here, and instead of a ball, I'm going to use this metallic plate, right? I'm working with a metallic plate. The dotted line is the illustration of the direction of when it's let go, and you can see what happens, how this metallic plate would move back, compressing the spring. Maybe the right way to do it is put the metallic plate here, compressing the spring, original length of both the spring and the string. So the original length, so I'm going to draw my spring as well here. This is the original length of the string and the spring. They're both getting stretched, and there's some compression. The elastic string may not take compression. The spring takes compression. So what happens here again, you have two forces balancing out. So T here is a sum of these two, but on your way back, now you'll have thrust force, again by the same equation, but x is now y, and it's the force that pushes the object down. So the rate at which velocity becomes zero here is now going to be slightly different. You'll have a steeper curve coming down, right? Because now you've got additional pressure against gravity. So actually, we'll have a less steep curve because gravity can't reduce speed just enough because someone's acting against this thrust force. So, interesting problems for you to work with. I encourage you to go through this in a little more detail. I'll come back now in a second and get into the next phase of our next thought process that you need. Before I leave you with on this, there's one more possible scenario I want you to consider. I have only looked here at a force applied with, let's say, either thrust or um, tension and gravity, but I can give you one other scenario to look at and play with, and this is an inclined plane with an object. And here we could do this in two ways. We can either do this in a manner in which, and this is very important, especially for people who do locomotives and other things, because when you're pulling something up, they normally tend to have springs along with they don't just pull it using a regular hard object because there's a shock factor to consider. There's often springs, and you can give yourself a spring here, right? And assuming this is a fixed point, there is no movement, and assuming this has a mass of m. Obviously, we know g, we know theta. Think about it this way. If I introduce friction with a coefficient of friction of mu, the spring has a elasticity modulus of lambda. Obviously, what happens, you're going to have to find out here. You add one more dimension to the force, which is the force. First of all, you resolve this force in this direction. So you get the sine theta factor. So you have the mg sine theta, right? However, and then of course you have tension or thrust, whatever's happening here. So you've got one more here. However, now you've got the added question around friction. And now it becomes really important, because if this thrust, or if this spring is compressed and there's thrust and there is this positive, if this force of gravity, the object's moving downwards, then friction would act in this direction, isn't it? That would be friction. However, if the spring was actually being stretched already, then there's tension, and mg sine theta is pulling it the other way. If I release the angle a tad bit and sine theta became lower, suddenly mg sine theta is not very powerful, and the spring's going to pull this box back. Then friction's going to act the opposite direction, right? So you could have that scenario too. So here I am just going to make this problem a little more complex for you by adding one, the sine theta component, the other, the uncertainty of the direction of friction until the forces balance out. Remember, that's why we did an entire lesson on friction. Friction can just be non-existent and instantaneously work against you because you've changed the direction of motion. So another area for you to play with the problem. Okay, this is done. So now let us come back to the final area I want to talk about here. You don't need all that. Let's give the formula. Let's come back to the final area, and I want to talk about what happens as we work on this string, right? Now I'll go back to my string, and I start here. Obviously, got this, and I'm going to yank it down, right? Relatively easy, but as I come out, it's harder and harder and harder and harder. So much easier to pull this, right? Much easier, and that's easy for you to see too, because t is a function of x and L is constant. So as x increased, as I've extended, further tension is also becoming harder, right? And tension's a force. What have I done? I've used some of my own strength to do this. I've applied some strength to do this. And I am applying a force. There is a force in there now called tension. But the application of a force over a particular distance means I did some work. Work means transfer of energy. So what happened to the energy? Now I've obviously spent the energy in doing this. That's exercising. I spent my energy. But energy is never destroyed. So energy is now transferred into this elastic string in some form, in a potential form, meaning it can act when it wants to act. And that action is when I let go, it acted. So there is potential energy. I want to bring this concept to you, right? And before we do that, let's begin the mathematics for it, right? So let's just say there is a force. So we'll go back here and we'll remove that. We don't need that, right? Now, actually, we probably want to not even confuse not even worry about gravity here, right? Let's look at this in a more straightforward way, okay? So I'm going to do this, and I have L, and I'm extending to X. Work with me on that, right? And that is done by the application of a force, some force vector F, which means the reactive force is building up inside, which is tension. So from here to here, my force has done some work. But as I'm doing that, because 10t is a factor of x, you can see it's increasing. So it's almost like saying, if I went to my favorite, and I said this is x, well, I should use like distance, but yeah, this is x, you get it. And if this is the force, which is of course equal to t, right? Because they're equal and opposite, so magnitudes are equal, so the magnitudes force is equal, right? So they're the same, really. What's going on here? As x increases, the force I put in keeps going up. And I could notice that because the slope of the line is lambda by L. So if somebody said, how much work is involved in pulling this string? Well, it's increasing with time because I was increasing with distance. So pulling it a little bit was very easy because I could just say, because if that was force, right, at any point, that would just be force and distance. That might be easy one, but how do I resolve? I mean, the value of my force is here. That's the force I've applied times distance. But how do I now rationalize this to work? And it's increasing with time. It's not constant. It's not like I could just take this value of force by F by X because it just seems like, well, at this point, would you just say it's there and just increase the rectangle? Not quite, right? And that's why while you can visualize it this way, perhaps the better way to say is if tension was a function of X, which it is, right? Lambda L by X, so it is a function of X. If I need to integrate at every point here, I'm going to have to look at every little, it's little rectangles that I'm going to have to do. So go to my integration, and I'm going to integrate between 0 to x dx. What have I done here? I've basically done force times distance, right? Force times distance, which is basically work. We know that from basic physics or what we've learned before. If I integrate this and now say that's lambda xl, lambda x by L dx integrated, which is nothing but, you should know this, lambda x squared by 2L and I apply the limits 0 and x, and what's the answer? It's basically 0 is 0. Your answer is here, right? So that's basically the work done. But what is this work doing? We saw that change, and we know, and because it's in this manner, unstretched, if I say that my string, this time I'm just going to do this to my string has no mass, and if the string of length L remain the way it is, there is no mass, it's considered a light string, technically no function of potential energy exists, it's not moving, no kinetic energy, net energy 0. By my doing this work, by my exerting this force, I have now stretched this thing by a distance x through the application of a force F. What have I done? I have somehow given this string, my work is translated here. I would now say, as the string stretched, it's, and watch the term, it's elastic energy. I have given it elastic energy. Well, the work applied, energy is not created or destroyed, so that's there. That's why I excluded gravity and came back to this motion, right? Because when you include gravity, there's more to worry about here, right? So there's elastic energy. But what kind of elastic energy is it? It stays there with the application of that. Once that force is applied, it stays there. Obviously, in equilibrium, there is a balance of what I'm acting as the tension, right? As soon as it goes, it reacts. So that means it's a potential energy. So what I want to call this really is elastic potential energy. You know what? There's a lot to write, so you might just see me do this EPE. You could argue that there is something called elastic kinetic energy, but this is a massless string. So remember, kinetic energy is mass times square of velocity divided by 2. So there is no real elastic kinetic energy. There's only kinetic energy because you have a mass at the end of the string. When it gets pulled, that one has kinetic energy, which is then getting elastic potential energy keeps dropping, because remember when it was here, there was nothing. When it stretched, elastic potential energy exists. Elastic potential energy is equal to lambda x square divided by 2L. That is then getting translated. So as x goes down, you can see it just drops very quickly. Where does it go? It's going into, if a mass was attached to it, it's going into the kinetic energy of that mass, right? That originally the chalk had no kinetic energy, velocity 0. When I let go, it speeds out, and that's the kinetic energy that's going. So when I now take our core concepts 3, 4, and build on that law of conservation of mechanical energy, I would be able to rewrite that and say that it's not just in the presence of gravity. Remember, there we said non-gravitationally elastic and kinetic and potential energies remain unchanged in the absence of any non-gravitational force. In this particular case, even if I had gravity here in this case, I could say that the kinetic energy of this mass, its gravitational potential energy, and the elastic potential energy of the string combined do not change. Pay attention. So that's my string. That's a mass m. I introduce the mass m. Guess what happens? We begin to see extension to this point of through m, right? That's my mass. Now I'm going to say gravitational force Fg is acting, and that's equal to m times g through the process of coming here, this object now, imagine this, right, has arrived at equilibrium, of course, so its kinetic energy appears to be zero, it still has potential energy. But there is something pulling back here, and that's the elastic potential energy. If the object was moving down this elastic spring, what was happening? Gravitational potential energy was reducing. The object had kinetic energy, but all of the potential energy did not go to the kinetic energy. We were building elastic potential energy. So gravitational potential energy. So in this area, let me just bring this out to you here, right? Maybe this is not the point of equilibrium. Maybe the point of equilibrium is further down. This is an elastic string of length L. From this point here, point A, when I've introduced this to point B, what happened? Right? The following happened. I'm going to take the work. You know the work function now, so I don't have to worry about it. We're doing energy. So from this point to this point, as we moved, the following happened. Gravitational potential energy, GPE, right? Assume we are somewhere here is ground zero, and somewhere here is H, the height. Just assume this is H. At this point, it's H minus L. So gravitational potential energy is mass times acceleration due to gravity, and its height, H minus L, right? That's changing, right? Let's say we've moved X here. So L plus X. So H minus L plus X. So gravitational potential energy slightly changed. So delta gravitational potential energy. Where did this go? It gave it kinetic energy, but object is moving down, right? Whatever be its velocity. So kinetic energy, delta, has gone to increasing. So this is a reduction. This is a vertical fall. So this reduces a reduction of potential energy. Gravitational potential energy, GPE, is what does it have? What's happening? It's getting translated to velocity. We saw that in the example of a free fall. So it's delta kinetic energy, not gravitation, right? This is an increase. Okay? This is an increase. And where is it going? It's not free fall. There's something holding it, and that something has a little tension. And that's building up delta elastic potential energy. That's increasing too. And remember, all of this is valid only until the limit of elasticity is reached, at which point the string snaps, gravitational potential energy begins to get fully converted to kinetic energy, the object accelerates due to gravity, and blah, 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 the life that we already know. But here we go. We have this. Which means I can write all of these together and now say the law of conservation of mechanical energy can be written as delta kinetic energy plus the sum of elastic potential energy, right? And this is a reduction, meaning this is a negative sign. Comes here, becomes positive, plus delta gravitational potential energy is equal to zero. The conservation of mechanical energy is restated. Why is this positive here? Because here's a reduction. I wrote reduction here, right? So it would be an effective negative sign because it's made of anything made with velocity, anything with acceleration. They're all vectors, they're positive. So the sum of these changes is zero. So to make this valid, GP goes here. GP would get a negative sign, which makes sense because it's got it's reducing, right? So that is important. So in reality, I should write the negative delta is equal to that. So you'll see this. Okay, this should be clear. I hope it's very clear. You now have a formula to calculate that. Kinetic energy is easy. Half mv square. Gravitational potential energy. You should know that too. You can now estimate what happens. And here is what I'll leave you with a very interesting problem, and this is the all too familiar problem of. So I'm going to bring gravity and energy, and this is a concept around the conservation of energy, right? So I want you to do it, think about it this way, and I'll kind of give you an overview and I'll leave you with it. So here we are. I'll try and draw this. This is my cliff, the bottom of the cliff, whatever canyon, and then this is all water, right? This is all water, and obviously here I have a bridge. That's my bridge. And right here is your friend who's invited you as he wants to open a bungee jumping adventure. So here's what he tells you. He tells you, hey, that is my total height. I can measure that with a little sensor. Got it. I'm not going to allow anybody who's heavier or has a mass higher than 100 grams. So my max mass is, let's say, 100 kilograms. Actually, for the purpose of this, let's just say mass is m. Use this. This is a good way to do this exercise. Mass is m. And he says, hey, I have all these different strings, all of modulus of elasticity lambda. And he asks you, because you really know physics and math, what is the length L, natural length? Remember the term natural length. This is the modulus of elasticity, mod elasticity. What is the natural length if the maximum m gets on this bungee jump and just touches the water? I obviously know it's water, so it's safe. They can make contact, so they can touch this. How would you do it? Which simply means the maximum extension is x. That's one way of looking at it, right? So I'm going to give you the idea of how you do this. You could define a maximum extension x such that L plus x is equal to h, right? That's maximum extension possible by this mass. You could do it that way. But if you applied just the force equation to do that, you might be mistaken, because what happens is there is a kinetic energy component, because when you jump from here, you're racing down, you're building a lot of velocity, and there is an energy factor to consider. So I wouldn't just do the force equation, but you can work with this as x. You can work on that and try and estimate it from that point of view. You know lambda, so you know the tensile strength that comes back to whatever x value comes in there. So that's another area you could look at. But I would really encourage you to look at the buildup of elastic potential energy, the change in gravitational potential energy, assuming that this is ground level and that's where you want to make your base zero, right? So if you want to do that, it's safe enough. Of course, if they hit it, gravitational potential energy becomes zero. It's massive kinetic energy, that will continue to send them down the water. But yeah, we'll worry about that fate on the day your string snaps. But I don't know, snaps. And for this problem, you are operating within the limit of elasticity. This is very important, right? Because the moment your string snaps, everything goes away. So within the limit of elasticity, find this. This is what you need to find. This is given. This is given. You know G is all times. You don't need a value for it. H is given to you. How do you write L in terms of H? So you can tell your friend that, hey, if you are H meters above the ground, your length To support a person of mass m with on a material of modulus elasticity lambda, what will your L be? And I would like you to find out, and I think your answer should look something like this, if I'm not mistaken. I'm not asking you to derive a formula. I want you to do the math behind this. The hint is in the energy equation. Your L should roughly be equal to H divided by, and what you should get here would be something to the tune of 1 plus, I would think the force is mg, so it's mg over lambda. And I think you should see, because you're doing kinetic energy, which has a square of velocity, which you will normalize, you should see 2. And I think the force here would again be mg lambda plus, and I think your result should be very close to this. And if it is, you can be assured that you are pretty much set for a further level, further mechanics, A level elastic springs, dynamic problems, and elastic energy problems. You should be good. If you can derive this or get to this relationship by looking at an object of mass m using a string L that's jumping off this height h on a string of modulus velocity L, and you can arrive at this kind of a relationship roughly. And remember, the hint is in the energy. The hint is in also knowing that this is nothing but a force. And when I normalize this force to with lambda, I'm getting a function of ratio of distance. So you see that I'm kind of giving you the mathematics behind it. And because there's a square on velocity and energy, when that square goes away, a root comes in. So I'm just giving you some hints. You work it out. It should be a fairly interesting exercise. But that is the important parts with dynamic problems on elastic strings and springs and how elastic potential energy is defined. Hopefully, it was fun. It's a lot of fun, this subject. Hopefully, you enjoy working this out, and I'll see you in the next video.